I debate whether or not I should leave this. I'm going to probably use the projector someday, but not yet. Okay, so let me go back. So here was one of the little bits that was hanging from the last section, lemma 7.3.15. And this lemma connects for a linear transformation T from vector space V to vector space W with dimension of V equal to n and the dimension of W equal to m. And then we let phi beta be mapping from V to Rn. This is a coordinate mapping for V. And take phi gamma from W to Rn, or for Rm as coordinate mapping for W. So obviously I'm assuming that, I'm assuming that beta is the basis, and for V, and I'm assuming gamma is the basis for W. Okay. Now, if all that's true, then I can relate the null space of the matrix for T to the kernel, something about the kernel of T. So let me just state the theorem, and then we'll prove it. And so here it is: the null space of the matrix of T with respect to the basis beta gamma is actually equal to the image under the beta coordinate mapping of the kernel of T. That's point number one. And point number two, the column space of the matrix of T, all right, is equal to the image under gamma of the range of T. This is an interesting lemma because what it's doing is it's relating this concrete null space or column space. These are statements about column vectors, right? To something about this abstract linear transformation where we're talking about kernels and ranges, right? Okay, so let me go ahead and prove the first one, and then I will try to look at an example of this that we can play with today. So how do I prove the null space of that matrix? So let's work on one. Let's see here. So let X be an element of the null space of that matrix. All right. All right. What's that mean? That means the matrix T beta gamma times X is equal to what? It's equal to 0, right? That's the definition of null space. Now, of course, then the question is, what's the kernel of T, and what is this matrix? Since many of you have not watched the video, you don't have any idea what I'm talking about. It's unfortunate, but true. Oh well, the show must go on. So this matrix T beta gamma is defined by what? I defined it as follows. I said that, there's different ways to define it. I'm trying to remember here. Oh, I usually end up having to draw a picture. Try not to do that. Let's see here. How to relate T to the matrix of T. Yeah. I'm going to draw the picture because we need it at some point anyway. So here it is. Here's V. Here's W. T goes from here to here. Here's the beta coordinate map, which trades V for Rn. And the gamma coordinate map trades W for Rm. So Rn and Rm are pictures under the coordinate mappings beta and gamma of V and W respectively. Oops. So down here, you have a matrix multiplication, the linear transformation which is induced from that matrix T beta gamma. Okay, so let's see here. I could also, I could trade that, equivalently what? Let's state it in terms of a linear transformation. I can write L of that matrix acting on x equals to 0. I've just changed language a little bit. Remember what L of a submatrix is? This goes back to fundamental theorem of linear algebra. I'm just using the notation we used earlier, like L sub A of x is equal to AX, right? You forgot. I still use that notation. Okay, so, but L of beta gamma I can also look at in terms of this path. All right? So I can, by definition, essentially, L of T beta gamma is equal to what? Well, so I start by going T beta inverse. That's the first, mega style here, folks, because we're in composition, so the first is last. So T beta inverse. And then T takes me from V over to W. And then T gamma takes me back down again. All right? So what I have then, this is the relation between T and L beta. Let's see here. So what I could do is, what I do here? Do a lot of different things. I'm trying to get my hands on something about the kernel as it relates to this point x. I'm trying to show that x is in the image of the kernel of T under beta. Let's see here. What's this say? I could, let's see, what could I do? I could operate both sides by phi gamma inverse, see what that takes me. So phi gamma inverse goes with L of T beta gamma is equal to, so if I compose both sides with phi gamma inverse, which I can do since it's invertible, these cancel, and it just leaves me T composed with phi beta inverse. Right. All right. So what happens if I operate on x both sides? But what? Phi gamma inverse of L of T beta gamma of x, right, is equal to T of T beta inverse of x. Now this x, what did we know about it?
It's in the null space.
It's in the null space, so this, on the left-hand side, this whole thing is what, 0, right? As in 0 in where? Just to keep track of things, in Rm, all right? You can M by M matrix, multiply by n component vector, out pops an M as a dummy vector. Now, this phi gamma inverse is linear transformation. What's the image of 0 under a linear transformation? 0. Yeah. So we have this 0, right? Okay. What's that say about what does that say about this element right here? So this is all equal to 0, right? Therefore what?
It's part of the kernel.
Right, therefore phi beta inverse of x is an element of the kernel of t. The kernel of t, by definition, folks, is b in b such that t of b is equal to 0. Just in case you forgot the definition. All right, so we've got that phi beta inverse of x is in the kernel. So what does that say about the, what's it say about the image? Thus what? Thus phi beta of phi beta inverse of x is an element of phi beta of the kernel, right? But what? However, phi beta inverse is what? It's just x. So what have I shown? I've shown that if x is in the null space of this matrix, then it's in the image of the kernel of that matrix. Now, to show that they're equal, I have to reverse the argument. I think I've spent enough time on this. If you really understand what we just did, you can prove the rest of these assertions, but it takes some time to do it. I want to do examples and stuff today. I do want to draw you a picture of what's going on. So what's happening here, right? You can think of the null space. What is the null space of the kernel of T? Where does that live? The kernel of T is a subspace of the domain of the linear transformation T, right? So you could envision, if this is 0, right? You can envision the kernel of T as something like this. Kernel of T is something up here, like that. And then we proved that under a linear transformation, the image of a subspace is again a subspace, right? So in particular, the coordinate mapping phi beta is a linear transformation from V to Rn. So it maps this subspace kernel of T to a new subspace, all right, down here, suppose this is 0, right? And so down here, maybe just a sort of a picture, this is the image under phi beta of the kernel of T, right? So it maps the kernel down to this other thing. That other thing in Rn is precisely the null space of the matrix. It's kind of what you'd expect, right? On the flip side, if you look at, really just a second. On the other hand, the other part too says, you know, the range, it doesn't have to be all of W, right? It could be like some one-dimensional subspace for F, for example. And what this theorem says is that the range of T is mapped under the codomain's coordinate mapping down to something over here, right? Which we can identify with the column space of the matrix of T. So there's a connection, right, between kernel and range, right? And between, there's a connection between kernel and null space, and there's a connection between the range and the column space, right? Yes, Len?
This is just a random question, but the kernel, does that have anything to do with the fiber? I remember reading that somewhere.
Yeah, the kernel is the fiber over 0. Yes. So this is and also a fiber is the inverse image of a singleton, the inverse image of a single point. Don't get lost in the language. It's just the set of all points which maps to 0. It's nothing. Don't make it more than it is. So, but here's the thing. Here's the thing, though. If I chose a different set of coordinates, right? Because the choice of basis is not unique, right? So if I chose a different set of coordinates, you know, let's suppose I chose a beta bar coordinate system and a gamma bar coordinate system, what would happen? On my picture, I'll denote it in black. So if I had yet another basis choice, all right, and you know, maybe I have, let me get rid of the blue, I don't need that anymore. clutter my picture a bit. So if I had another choice of basis, right, if I had a phi beta bar coordinate system, and if over here I had a phi gamma bar coordinate system, then I could, instead of looking at this in terms of the beta gamma coordinates, I could look at it in terms of beta gamma bar coordinates, and I could look at L of t, beta bar, gamma bar, right? But this theorem doesn't respect the choice. I mean, beta and gamma is just a choice, right? The same proof goes through in the barred coordinate system, right? So it's still going to be true that the kernel maps to the null space of the barred t beta bar, gamma bar. And it's still going to be true that the range of t maps to the column space of the new thing down here. So but here's the interesting thing. So, they don't have to be the same set, is the interesting thing. So, that would be something like phi beta bar of the kernel of t. And over here, you have something like phi gamma bar of the range of t. And again, the interesting thing is that doesn't actually have to be equal to phi gamma of the range of t, because these are different coordinate systems. However, there is something that's common to both of them. They both have to have the same dimension. So the subspaces could look different, like the null spaces could be different for different coordinate systems, the column spaces could be different for different coordinate systems. But the thing that they share in common is they will both have the same dimension, right? Because the dimension of the null space of the matrix, the dimension of the column space of the matrix ultimately rests from what? It ultimately stems from the dimension of the kernel and the range of this t up here, which is independent of the choice of coordinates. Yeah.
Is there a more, maybe this is a stupid question, but is there a more geometric way to think about all this? Or is it not really possible?
Well, I'm talking about abstract vector spaces at the moment, and let's look at an example. And I'll just figure this example.
Appreciate it, thank you.
I think that will help. Excuse me. If I have t of, let's say, try to keep it relatively simple, a plus bx, all right, equals to, let's say, goodness gracious, I need some kind of thing. How about this? A, B, B, A. All right, so here, t is mapping from first order polynomials to W, which is a subspace of R2 by 2, where this W is what? W is the span of gamma, and I'm saying gamma is equal to, what is it equal to? It's 1, 0, 0, 1, 0, 1, 1, 0, my choice. Okay. Oh, well, the kernel here isn't going to be very exciting, but you guys can forgive me. Oh man, we're not going to be able to see this theorem at all in this example. I need to do something stupider. How about the mapping is, let's say A plus B, 0, 0, A plus B. And I'm going to let W be the span of these two things. Okay? Yeah. Now it starts to get interesting. So first of all, what's the matrix of T? And so what's the, I need to give a choice of basis over here. Let's say beta is equal to what? 1x is a good choice of basis for P1. So I do my usual thing, A plus bx. The T mapping takes it over to A plus B, 0, 0. Okay, under the beta coordinate mapping, excuse me, we have AB, that's equal to so the coordinate of I'm calling A plus bx B just to give it a name. So So the coordinate vector of V is just AB. This guy over here would be the image of V under T, TV. So under the gamma coordinate map, down here you have, well, I don't know. What do you have? What are the coordinates of TV in the gamma basis?
A plus B and 0.
A plus B 0. Now, how does Daniel know that? He has observed that T of B can be written as A plus B times 1, 0, 0, 1 plus 0 times 0, 1, 1, 0, right? So that makes the coordinates of T of B under the gamma basis as A plus B and 0. Yep.
Never mind, but I think it's something.
Now, to find the matrix that goes from one space to the other, here like so, I need what I need. So my question is, what's my T of beta gamma for this example? Basically, I need to fill the blank here. This matrix times AB is equal to A plus B and 0. So 2 by 2 matrix, what do I put there, guys?
1, 1,
1, 1. Yeah.
0, 0.
Great, indeed. And there you go. So we just figured out what the matrix is of T with respect to the beta gamma basis, right? Now my question to you is, what's the null space of that matrix, and what's the kernel of T? Your work on kernel of T real quick here. So what we're asking is A plus Bx such that what? Such that T of A plus Bx is equal to 0, right? But that's what? That's A plus B, 0, 0, A plus B. So what does this basically tell us? This tells us that what?
And B are equal to 0?
Right, A, well, no, it tells us A is equal to minus B. So the kernel of T actually is just going to be A times 1 minus X, such that A is a real number. Because B is equal to minus A. My choice. I mean, it is A equal to minus, I said A is equal to minus B. I guess I should have, whatever. I mean, fine. Sorry it's bothering me. I basically used B is equal to minus A here to get rid of B. Fine. How about the null space of this matrix? What's the null space of the matrix T beta gamma? So basically this tells us what x1 plus x2 is what? 0. So if you look at the thing in the null space like x1, x2, you have x1 comma minus x1, such that x1 is a real number, or if you like 1 minus 1, such that, times t, such that t is a real number. I mean, whatever floats your boat. What if we use different coordinates? Can you guys think of a different coordinate system you might use for W? Yeah.
Never mind.
What did you write such that 1 comma negative 1t
to the right of you. Standing right by you.
Oh, sorry. Yeah. Yep.
Well, is there some way, I mean, I guess you could expand like the one that's already up there, like A plus B times 1, 0, 0, 1.
Well, I mean, I'm asking, is there another choice of basis for W? What, I mean,
Yeah.
Well, if you have like,
Yeah.
I mean, you can just do 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0.
well, I want a basis for W. W is two-dimensional. Right.
I mean, you could have taken one of the ones and put it on the other side.
There's really no like single right answer here. Here's the lazy answer I would use. What I would do would be just add them. So, and subtract them. So each one of these is formed by a linear combination of those. So they'll have the same span, right? That's another choice of basis for W. And then the question is, what's the coordinate, you know, once I make that choice, my question then is, what's T of B gamma bar then? Now it's not immediately obvious, right? We're gonna have to do some work, if you'll allow me to erase this bit right here and work in this bubble. So to solve the coordinate question, the coordinate bar, so what I'm looking for is A plus B, 0, 0, A plus B equal to what? So that's the question, equal to say C1 times 1, 1, 1, 1, 1, plus C2 times what? 1 minus 1 minus 1, 1. Right? This will be T of B. Words. TV gamma bar will be equal to C1, C2, right? So can you tell me what should C1 and C2 be then? So help me if the coordinates are the same, I'm going to scream yes.
have not, I don't know.
Look, you guys gotta be, you know, this is not, don't be scared, this isn't that bad. You just gotta work it out, right? So we got what, C1 plus C2, C1 minus C2, hey, that's nice. What does that say, the off-diagonal components of these equations, what do they tell you?
They are, well, I mean, C1 is equal to C2.
Right, C1 is equal to C2, but these ones tell us what? So C1 is equal to C2 and what else?
2,
2 C1.
C1 equals A plus B.
That would be 1/2 A plus.
Right, so C1 is 1/2 A plus B, right?
So it's
C2. So apparently, let's get rid of the question mark. Here's what it is. It's 1/2 A plus B, 1/2 A plus D. So, I'm gonna go back here now, right? And I'm just sticking with the, I just to keep things simple, I'm not gonna change the basis in the domain, all right? So I changed the basis in the range to gamma bar. So let's see, here's this. What's over here now? TV gamma bar is 1/2 A over 2, B over 2, A over 2, B over 2, right? So the matrix here would be what? It's a half, a half, a half, a half, a half. I think it's all halves. Oh man, well this is a, shucks. The null space is still the same, my dumb luck. I guess the 2x2 matrix, but I mean, you can't, maybe you can't see it yet, I see it already. If I look at the null space of this guy, E beta gamma bar, That's the null space of a half, a half, a half, a half, right? And so basically I'm studying the equation x1 over 2 plus x2 over 2 equals to 0, right? And so we're going to get back to the same. We're going to get back to here again. But my point to you is it could have been different. If we had a higher dimensional example that, you know, I spent a long time on, we had higher redundancy. All right. So, in part, this is why I wanted to talk to you about coordinate change. Is coordinate change will give me the natural tool to understand a result like this. And for example, like why isn't there a why isn't there a coordinate dependence? It's because if I change coordinates, there's a really simple way that the new matrix is related to the old matrix. All right, so let me just get to it here. I've obviously spent far too long on that example, but I think it's probably, oh no, it's fine. I was going to do it. It's not your fault. Anyway, it would be your fault. It's always okay to ask questions. So good night. You know, eventually I want to learn how to use this thing. Somewhere there's a full, oh, there it is.
How did you do it? Or
All right. Go back from the future. Start at the very beginning. So, the problem we're starting to ask about is coordinate change. How does coordinate change work for a vector space? This is, you know, as I've shown you, even for a simple example, it gets kind of, it's a pain. I think, does it show up decent enough in this way? Yeah, okay. We make it a little bit bigger. Deluge nature is in the screen. Last time it was slightly out of the screen. Is that okay?
Yeah.
It's not okay. All right. So the basic idea here of coordinate change is if you look at an abstract vector space, right? There's a thing like this a plus bx, right? A plus bx, whatever that is, it's the same whether I express it with respect to my basis, you know, 1x. It'd be the same if I express 1 plus with respect to the basis x1, or with respect to the basis x plus 1, you know, x minus 1, et cetera, et cetera. Whatever my choice of basis is, that doesn't really matter. Whatever my choice of basis is, the point in the vector space itself should exist independent of that choice, right? So like x, a point in the vector space, it should be independent of my choice of basis. So if I have two bases to express it, that means I've got two different ways of reaching this same geometric object, just expressing it in terms of different choices of generating sets. So for example, and I'm going to try to use unbarred and barred just to have two different coordinate systems. I think it's easiest to express if I have a very similar notation but just slightly different. That's my approach here, is to use bars for the other coordinate system. So, excuse me.
You all right?
Not really. So here's with respect to the beta system. Here's with respect to the beta bar system. That's x bar, v bar. If you really have an imagination, and I guess I should make it bigger.
Mm-hmm.
All right. So my point to start with is that I can express x either in terms of the v coordinates, I mean in terms of the basis v1 through vn, or through the basis v bar 1 through v bar n, right? But x is x. So I have that x is equal to, on the one hand, the inverse image under the beta coordinate mapping of the beta coordinate vector. On the other hand, it's the inverse image under the beta bar coordinate mapping of x bar beta. But those are both x, so they're equal, all right? Yes?
And the reason x is independent of everything is because if you're like in beta, you have v1, but then the scalar coordinates are defined there. But then if you go to beta bar, those scale coordinates in the, like D1, D2, bar, like,
Well,
they change relation to each other, they should go the same, right?
Well, that is also true. I mean, somehow, you're asking how it is that these can be equal. It's because the coordinates and the basis, they're adjusted in kind of inverse ways, but more fundamentally, it's because X is a point in a vector space. What does that have to do with my choice of basis? It doesn't. Right, the basis is something different. X is a point in the vector space.
Yes, it'd be there regardless of what basis you choose, as long as the basis fits the
Precisely,
basis.
yeah. So that's why these have to be equal. But then I can operate both sides by this mapping, phi beta, and then phi beta inverse gives me back the identity, which leaves me, oh, I think I'm sorry, opposite way around. I operated both sides by phi beta bar, and so that solved, I'm basically solving for this. So I solve for that, and there it is. Voila. That is the relation between the beta coordinates and the beta bar coordinates. They're related by the composition of phi beta and phi beta bar and phi beta inverse. Need a notation for that, and this is the notation I'll keep using for this section. I say that phi beta bar, this is the coordinate change map to start with beta coordinates and change to beta bar coordinates. Here's the real important calculational formula right here. The coordinates in the barred system are equal to the coordinates in the unbarred system times the change of basis matrix, phi beta. Now, all of these things, if you lose track of things, you can see in this picture. I mean, this is the essential truth. There's this point X up here. I can take X and I can look at it in one picture in the beta coordinate system. That's one picture of X. Or I can take X and I can look at it in terms of the beta bar coordinate system. That's a different picture of X. But these are just like, it's the same, it's the same duck, it's the same cat, it's the same rabbit, whatever you want to think of it as. These are just two different pictures of it, right? And you can change one picture to another by this change of basis matrix. Multiply by p beta bar. That takes you from this guy to that guy. So now how do you actually find this change of basis matrix? For an actual given pair of bases for an abstract vector space, it is a pain. It just takes calculation, all right? I want to feel your pain, so here's an example. So here I have the set of traceless 2x2 matrices. All right, A11 plus A22 is 0. That means the trace of the matrix is 0. And I pick one basis for B, and I pick another basis for B. And then I just go to the task of calculating the change of basis matrix. So to do that, what's this going to be? So P beta bar was equal to what? The matrix of what? B composed with which B inverse? Beta bar composed with beta inverse, all right? So if I want to figure out, this itself is the reason it's reasonable to write this, I'm saying standard matrix of this. You notice that phi beta inverse composed with phi beta bar is a mapping from Rn to Rn, right? See that? Phi beta inverse is going from Rn to V, and then phi beta is going from V to Rn. So phi beta bar composed with phi beta inverse is going from Rn to V back to Rn again, right? So all said, it's a matrix, it's a transformation from column vectors to column vectors, which means I can calculate its standard matrix, right? How do I calculate the standard matrix? I do what? No, go for it, what do you say?
Can you just use multiplication?
Use multiplication of matrices, essentially, but we had a go-to formula, like, I want to find the first column in the standard matrix for T. What do? I look at T of E1, right? So I'm just using that trick here. To find the first column in the matrix, I look at phi beta bar composed with phi beta on E1, all right? Now, how do you define the, I talked about this more in the videos that some of you have watched, but if beta is equal to v1 vn, the real definition is the beta coordinate mapping. What does it do? It takes the abstract basis vector vj and it trades it for a standard basis vector ej. So this is what the coordinate map does: is it converts the abstract basis to the standard basis, right? And the inverse, and then you extend linearly. The inverse is this. In other words, the inverse coordinate mapping trades your standard basis for the abstract basis in the same way. So that's how I make this calculation over here. See this right here? I go v beta inverse E1 is E12. How did I know that? Well, it's very simple. That's the first vector in the beta basis. So that's why I put E12 here. E2 is E21. E3 is that gives me the third abstract basis vector in beta, which is E11 minus E22. And then I have to, this takes a little insight to show that, but so this is v bar 1, v bar 2, v bar 3. Anyway, there's a little calculation to get from here to here, and from here to here, and from there to there, but, well, actually from here to here, it's simple. That is e bar 3, right? It's E11 minus E22, E11 minus E22, so that's v bar 3. Just straight up is. Anyway, once that's done, column 1, column 2, column 3 in the change of basis matrix, like so. And then, so that's it. Now, I think it's better if you actually see how it works though, right? So I take a matrix. Here's a matrix A, 1, 2, 3, minus 1, which is, that's the matrix which has coordinate in the beta system, 1, 2, 3. Right? Oh, I'm sorry, I can't do math. 2, 3, 1, right? Because the first one was what? E1, 2, which is where the 2 is. The second one is E21, which is where the 3 is, so that's why I had 2, 3. And then the 1, because the last thing in the beta coordinate system is the E11 minus E22. So there's the coordinates of A with respect to the beta system. And so I take the change of basis matrix times that, and that gives me 5/2 minus 1/2, 1. Allegedly, that is the coordinates of A with respect to the beta bar system. Yes,
If
sure.
it's E11 minus E22, would it be a positive 2 in the last coordinates to be 1 minus negative?
Did I go backwards? You might be right, I think. E11 minus E2, well, minus E22 though. So I've got the 1 plus 1 and minus 1, so I think it should be 1. You think it should be
But
1?
you have like a minus in there, and then that's a negative, so isn't it a minus and negative?
Minus where?
Up at the top.
E11 minus E22,
Yeah.
where it's minus E22, but E22
Oh,
is
okay,
minus
but
1.
E11 minus E22 is this matrix 1, 0, 0, minus 1, right? And I'm telling you that if you look at A, that's the component. I mean, A is just, it's got a 1 and a minus 1, right? So it's one of those things. I mean, just to be gory, A, I mean, to be explicit, let's see here. 1, 2, 3, minus 1. Thankfully in math, explicit has a different meaning. 2, 0, 1, 0, 0, plus 3 times 0, 0, 1, 0, plus 1 times 1, 0, 0, minus 1. So for that reason, the coordinate vector of beta, of A with respect to beta is 2, 3, 1. Right? Now I'm claiming, if you trust the math, that this is the change of basis matrix, I mean the change of coordinate matrix. It's called the change of basis matrix, but if I multiply this, I get 5/2 minus 1/2, 1. That's supposedly A with respect to the beta bar system. Now how do we check if that's right or wrong? Well, if it's right, then when I calculate the inverse image of that coordinate vector, I should get back A, right? So the inverse of this, I take 5/2 times the first thing, minus 1/2 times the second thing, and plus 1 times the third thing in beta bar. But if you add these things together, you get back A, and as you can see, it works. So. All right, so coordinate change in the abstract case is kind of a pain. But for columns, right, if you just consider the special case, suppose you're changing coordinates in Rn, everything gets a lot easier there. All right? Yeah.
Misspelled is off.
I don't think you can misspell this off.
That's a good point. It's HU is easy. Where's that?
No,
Where's
Right,
the
right in the red
That's
box.
fine.
Yeah, it's HU.
sorry, I.
You also, is that an exclamation mark?
It's like we should just do a straw poll. How many
Yeah, but
think it's
it's
HU? How many of you think it's HA or something? But that'd be
Alright.
wasting time, and I don't want to do that off the cuff because I realize we have a lecture to get to.
That's true. So for column vectors, right? For column vectors, you can actually express X as the basis matrix times the coordinate vectors. Now this basis matrix is nothing more than the basis V1 through Vm just glued together to make a matrix. Now I couldn't really do that in the abstract case because I don't know how you glue together, you know, polynomials to make a matrix, unless you're going to work with matrices of polynomials, which you could, but we don't. So in the case of, this is special, right? Special coordinate. We're talking about column vectors, changing coordinates for column vectors. You have these like awesome formulas. To find the coordinates of X with respect to the beta basis, you just take, basically what this is you just string out the abstract, you know, the abstract basis for Rn, not abstract, the non-standard basis for Rn. You invert that matrix and multiply by X, and there are your coordinates. It's simple as that. And so to relate the beta bar coordinates to the beta coordinates, you just end up taking the basis for the bar system, inverting that matrix, the basis for the beta system, and multiplying them. That gives you the coordinate change. Let me show you an example. So like here, that's how to do it. Here's an example though. Suppose I'm looking at R2, I've got basis 1, 1, 1 minus 1, and 1, 0, 1, 1. I want to compare coordinates in these two different non-standard bases. So this is meaning of matrix, the beta matrix. You just take the, see what you do? You take the vectors in beta and you just put them as columns. See that? The basis for gamma basis matrix, you put the vectors in gamma as columns. And then, well, these are 2 by 2, right? So you can invert them. We have a formula for that, right? We don't have to calculate further. We just use our standard 2 by 2 inverse formula. And so there they are. So I can calculate, for example, what's the coordinate of V? I take V equals to 2, 4 just for the sake of discussion, all right? So if V is 2, 4, what's its coordinates in the beta basis? So I just take beta in the inverse of the beta coordinate matrix, basis matrix. Multiply that, I get coordinates 3 minus 1. And the coordinates for V gamma in respect to the gamma basis minus 2, 4. And then I even calculate the change of basis matrix here, ends up just being the inverse of the gamma matrix times beta. And so I can compare my answers and by the change of basis matrix, and of course it works. So. But you notice what wasn't here? There's no polynomials. There's no I don't have to do any hand-to-hand combat with specific equations. I can just put column vectors in particular matrices and invert them and multiply them. It's all very kind of formulaic, which is not true in the abstract case, right? In the abstract case, you really have to kind of think through the diagrams. At least I do. Here's a picture of what just went on. So the vector 2, 4, right, is this point geometrically in space, right? So I can either reach it by, so you're asking for something geometric at the start, Christian, I finally give it to you. So I can either reach the vector 2, 4 by using the standard basis, right, and doing this vector decomposition, 2 in the x-hat direction, and then 4 in the y-hat direction, when I think back in terms of physics. Or I can build that same point in space by adding together F1, which is 1, 1, and F2, which is 1 minus 1, like this. I need 3 copies of F1 and then minus 1 copy of f2, I get to the same point. We can add yet a third thing. I haven't even drawn the gamma picture, right? There's yet another way to get to this point by building with the gamma basis, which I haven't tried to add to the picture. You might try to add to it. It might add something to understanding. I don't know. Now, when you actually apply these things to problems, a lot of times what you want to do is not look at a specific vector like 2, 4. You want to look at like an arbitrary point, x, y. And you want to discover what's the relation between x, y, and say x bar, y bar. That gives you the coordinate change between the two different coordinate systems. Here, if I look at b equals x, y, those would be the standard Cartesian coordinates, right? I can ask what are the bar coordinates with respect to the beta basis. Well, all I've got to do there is multiply by beta inverse that, and out pops 1/2 x plus y, 1/2 x minus y. This is equal to x bar. This is equal to y bar. So I can figure out the coordinate change for this. And of course, you can invert this also. Anyway, as usual, I'm behind, but I will try to slow down next time and show you how we understand coordinate change for linear transformations. All right.
There's just so much that we're introduced to, like 2 weeks, like, I don't.
Yes, the best cure for being confused is to do your homework.